Okay, let's dive in. Every year, right, the coast just holds its breath. You see that swirl form over the ocean. And the big question, the critical one, is what's it going to do in the next, say, 48 hours?
Exactly. That window, that 2-day problem, as we call it, that's everything. It really can be the difference between, safety and real disaster. Life or death evacuations sometimes hinge on that forecast.
It's the absolute core challenge. And
hmm
our traditional models, the physics-based ones, I mean, they're amazing feats of science, incredibly sophisticated.
Oh, absolutely. Decades of work have gone into them, but they still hit these fundamental hurdles. They need to be fast and they need pinpoint accuracy, especially when storms do unexpected things. Rapid intensification, a sudden turn.
Right. Those things still catch us out sometimes, even with massive supercomputers crunching data. So, okay, what if there's a totally different way? What if AI, artificial intelligence, could just look at the storm, learn its behavior from, well, from history, and spit out a forecast?
And do it in minutes, not
Yeah.
hours.
Minutes instead of hours. And maybe
Yeah.
even be more accurate.
That's precisely the territory we're exploring today. We've been digging into sources about this new initiative from Google DeepMind and Google Research. They've built something called Weather Lab.
Okay, so our mission here is basically to give you a shortcut, a clear understanding of this new AI approach. What is it? How is it really different from what forecasters use now? What can it do? And maybe most importantly, what could it actually mean for keeping people safe for the economy during hurricane season?
And there are some, frankly, surprising claims and numbers in the material we looked at. Things like forecasts being maybe 140 kilometers more accurate several days out.
Or an entire forecast run,
Yeah.
the whole thing done in less than a minute. That sounds wild.
It does. But to really get why this could be such a big deal, you first have to appreciate just how incredibly complex these tropical cyclones are to predict. They're huge systems, right? Hundreds, thousands of kilometers wide.
hmm
And their general path, that's mostly dictated by these massive wind patterns across continents, the big atmospheric rivers, basically.
Okay, the jet stream, high pressure ridges, that kind of thing.
Exactly. But then you zoom in. The storm's strength, how strong the winds get, how much rain falls, its exact structure, that stuff depends on tiny features. Eddies in the eye wall, convection bursts. Things happening on scales smaller than a city block can affect this state-sized storm.
Wow. So it's like trying to predict where a giant ship will go based on ocean currents, but also needing to know exactly how every single tiny barnacle on the hull is affecting its speed right now.
That's a great analogy. And traditional physics models, they run smack into this problem of scale. You've got your global models, they see the whole Earth, capture those big steering currents really well. But because they cover so much ground, their resolution is coarse. They kind of blur out those crucial small details inside the storm that drive intensity.
So they get the general direction maybe, but miss the power.
Often, yeah. Then you have the regional models. They zoom way in, see the eye wall structure beautifully high resolution, but their view is limited. They can sometimes struggle to get the large-scale steering right because they don't see far enough outside their little box.
Right, it's a trade-off.
It's a fundamental trade-off. And this difficulty, this mismatch, it feeds directly into the 2-day problem, into that forecast uncertainty we still grapple with. You really need both the big picture and the small details.
Okay, so this is where DeepMind steps in with like a completely different philosophy. And they're showcasing it with this thing called Weather Lab. Looking at it, it's way more than just a website with cool maps, right?
Definitely. They describe it as a living laboratory. It's specifically designed as an open test bench for these experimental AI models, running forecasts pretty much in real time during hurricane season.
And what do you actually see there if you visit?
You get these side-by-side comparisons. They show different AI models they're working on, like WeatherNext Graph and WeatherNext Gen, which do global stuff. But the main one for cyclones, the one making headlines, is DeepMind's experimental hurricane model.
That's the one doing the 50 different scenarios.
That's it. It's what they call a stochastic model. It's built to generate an ensemble, a range of possibilities right from the start. And crucially, something they really stress for transparency, Weather Lab has 2 full years of archived forecasts.
Oh, okay. So you can go back in time.
Exactly. Anyone, you, me, an expert meteorologist, anyone can go back, pick a storm from the past 2 years, and see exactly how the AI's forecasts actually performed against what really happened. No cherry picking allowed. You can verify it yourself.
That's pretty important for building trust, I'd imagine. So, okay, they've got this public lab, Weather Lab. Let's pull back the curtain, though. What's the actual engine? How does this AI learn about storms? How does it work?
Well, the core idea is pretty radical compared to traditional methods. They use a single massive AI model, one neural network trained entirely on historical data. And it's designed to handle both the large-scale steering and the small-scale intensity stuff all at the same time.
One model does everything. No need for separate global and regional runs.
That's the goal. They fed it just a colossal amount of data, 45 years of reanalysis data, basically. Historical weather maps, pieced together from every observation available, plus really detailed best track data for over 5,000 past tropical cyclones.
Wow.
So it learns the relationships implicitly. It sees over and over how things like high-pressure ridges affect the track or how warm ocean water fuels intensification. But it learns these patterns from the data itself, not because someone programmed in specific physics equations.
Okay, pattern recognition on a massive scale.
Hmm.
But how does it get those 50 different forecast possibilities? That sounds different from just predicting the single most likely path.
Yeah, this is key. It uses something called stochastic neural networks. Stochastic just means there's randomness or uncertainty built in, so the ensemble isn't an afterthought, it's fundamental to how the forecast is made.
How does that work in practice?
At the very start, when it initializes a forecast, it creates 50 slightly different versions of the current atmosphere perturbed universes, as they put it. Then the AI model evolves the weather wind, pressure, moisture, all of it forward in time for each of those 50 universes independently, step by step, usually every 6 hours, out to maybe 15 days.
50 different weather futures playing out simultaneously.
Kind of, yeah. It's designed to embrace the chaos, the inherent uncertainty of the atmosphere right from the get-go. Remember Hurricane Sally back in 2020? It just wandered around the Gulf for days. A single deterministic forecast struggles with that. But an ensemble of 50 possibilities, like this AI generates, it's much better suited to capture that kind of weird, uncertain track and show you the range of what could happen.
So it's not just drawing 50 random lines.
Oh, definitely not. The source material uses a really good analogy. Think of a chess grandmaster. They look at the board, they don't just guess random moves. They see the position and mentally play out several plausible scenarios based on their deep understanding of chess dynamics.
Okay.
This AI does something similar with the atmosphere. It sees the current weather, the board position, and then it plays out a bundle of plausible future moves for the storm, guided by the atmospheric dynamics it learned from all that historical data. Those 50 members are meant to bracket reality and show you where the biggest uncertainties lie.
And what's the underlying tech that lets it do this? Learn the patterns and generate the ensemble so efficiently.
The breakthrough they point to is called a flexible generative network, or FGN. This seems to be the core innovation. It's inherently probabilistic. It's not just hunting for the single best answer. It's designed to anticipate and represent uncertainty by essentially injecting a controlled amount of noise or randomness directly into its calculations as it runs. And that allows it to generate those 50 diverse but still meteorologically realistic scenarios very, very quickly in one go.
And the really wild part about this FGN.
This is what blew my mind a bit reading about it. The FGN is trained only on predicting weather conditions at individual grid points on the map. Like, what's the pressure here? What's the wind there? One point at a time.
Seriously, just point by point.
Yeah. You wouldn't intuitively expect a model trained like that to understand how all those points connect across vast distances to form coherent structures, like swirling rain bands or a large area of falling pressure that defines a hurricane. Those are complex spatial correlations.
But somehow, it figures it out.
That's the magic, apparently. The FGN learns to capture these large-scale, physically consistent patterns of the structure of a hurricane without being explicitly taught the physics equations or the spatial rules. It infers them just by seeing countless examples of the individual data points.
It learns the whole puzzle just by looking at the pieces over and over again.
That's the essence of the AI insight here, yeah. And the result is, the forecasts you see on Weather Lab, they produce maps and storm tracks that look meteorologically sound, like they could have come from a physics model, even though the underlying mechanism is totally different. And, crucially, this whole approach is incredibly computationally efficient.
Which brings us to performance. You mentioned some big numbers earlier.
Right. Looking at the metrics they've shared from testing on recent Atlantic seasons, 2023 and 2024, the results are pretty striking. For track forecast skill, the AI's average error at 5 days out was 140 kilometers smaller than the benchmark physics-based ensemble model.
Wait, 140 kilometers, that's a lot, 5 days out.
It's a huge leap. The source compares it to compressing maybe a decade's worth of gradual improvement in traditional models into this one step with the AI.
Wow. For someone living on the coast, what does 140 kilometers less uncertainty 5 days before landfall actually mean?
It means more confidence earlier. Emergency managers can potentially narrow down the threatened area much sooner. That allows for smarter, more targeted preparations, getting resources in place, planning logistics, maybe issuing watches or warnings for a more defined stretch of coast instead of a huge uncertain zone. That extra lead time and clarity is invaluable.
And it wasn't just the track, right? Intensity, too.
Yeah, and intensity forecasting is notoriously the harder problem. But this AI model actually beat NOAA's own high-resolution regional model, HAFS, which is state-of-the-art, and designed specifically for hurricanes. It beat HAFS on predicting both maximum wind speed and minimum central pressure.
Beating a specialized physics model on intensity from a single AI model,
Yeah.
that's really something.
It is. And for storm size, the wind radii, which are crucial for storm surge predictions, the AI was matching the modern physics models. So the potential is there to improve surge forecasts down the line, too. The takeaway they draw is pretty bold.
Yeah.
The AI isn't just keeping up in key areas like track and intensity, it's actually leading.
Okay, accuracy is impressive, maybe even leading. But the speed, you said it sounded revolutionary.
This might be the most impactful advantage right now, practically speaking. A full 15-day forecast, generating all 50 ensemble members, takes less than a minute. On one specialized chip, a TPU.
Under a minute. Compared to
hours on massive supercomputer clusters for traditional physics models, and it's apparently about 8 times faster than even other AI weather models people are developing, orders of magnitude faster.
Okay, orders of magnitude. How does that speed help a forecaster on the ground or an emergency manager? What can you do with that speed?
Well, think about it. If a full forecast takes under a minute, you can update it constantly. Hourly updates. Easy. Computationally cheap. So you can feed in the absolute latest observations, new satellite images, data from Hurricane Hunter planes, weather balloons almost instantly. Your model starts from a better picture of reality, which should lead to tighter, more accurate forecasts as the storm gets closer. Plus, if the model seems to be going off track, you can spot and correct that bias much faster. Speed buys responsiveness.
Speed plus accuracy.
Yeah.
Yeah, that's a potent mix. So how is this playing out in the real world? Is this just Google's research project, or is it actually being used?
No, it's definitely being tested operationally. They highlight a crucial partnership with the U.S. National Hurricane Center, the NHC.
Okay.
Forecasters there are actively looking at the Weather Lab output, the live AI forecasts, right alongside their traditional tools, the GFS model, the European model, all the usual suspects.
So it's another tool in their toolkit, not replacing anything yet.
Exactly, augmenting what they do. And the early feedback mentioned in the sources points to one specific really useful thing the AI provides, these Doorknock alerts.
Doorknock alerts, what's that?
It's like an early heads up. The AI ensemble might start hinting at storm formation or strengthening before the system even gets an official name or classification from the human forecasters.
An early warning before the official warnings.
Kind of, yeah. They gave a specific example, a disturbance, what they call an invest, near Barbados late last August. 4 days out, T-minus 96 hours, the traditional models just showed a generic tropical wave, nothing too alarming yet. But the Weather Lab mean ensemble forecast, the average of its 50 runs, was already painting a picture of slow development towards potentially a Category 2 hurricane near Puerto Rico. That kind of early signal, that Doorknock, gives the human forecasters a reason to say, let's watch this one extra closely. Much earlier than they might have otherwise.
And that comes right back to the 2-day problem, doesn't it? Getting that earlier hint gives islands, coastal areas, just precious extra time.
Absolutely. And that extra time isn't abstract. It translates directly into lives potentially saved, evacuations being smoother, and huge economic savings. There was a World Bank study mentioned, estimated global losses from cyclones since the 70s at $1.4 trillion.
Brilliant. Wow.
Yeah. So if better forecasts and warnings, maybe boosted by AI like this, could cut those losses by even, say, 5%, that's $70 billion. Real impact.
That's staggering, $70 billion. Were there other specific cases where the AI really showed its potential?
Yes, they discussed Cyclone Alfred in the southern hemisphere, February 2025. It was a strong storm off Australia, Category 3, and the traditional models were really uncertain, kind of split on whether it would stay strong or weaken too slowly.
Okay, tricky forecast situation.
Very. But the AI model, viewed through Weather Lab, Nailed it. It correctly predicted days in advance that the storm was going to collapse pretty suddenly.
What did the AI see that the others missed?
The AI ensemble clearly picked up on dry air getting sucked into the storm, which basically choked off its thunderstorms and caused it to fall apart fast. And it also pinpointed the much weaker landfall location, more like tropical storm strength near Brisbane, again, days ahead.
That must have completely changed the game for emergency prep.
Totally. Instead of prepping for a major hurricane hit, they could refocus efforts on the flooding risk from heavy rain at the right spot, knowing the wind threat was much lower. That kind of specific foresight is gold for decision makers.
Of course, you need people to trust this new thing. How are they handling that?
That's critical. They mention a growing list of outside partners, places like Colorado State University, the UK Met Office, University of Tokyo, Weather News in Japan, who are independently testing and verifying the model's performance. And they're working on explainability, trying to understand why the AI makes the forecasts it does. But early signs are good, like the fact that the spread in the AI's ensemble seems to genuinely reflect the real-world uncertainty.
So Weather Lab isn't the only AI weather game in town. How does it fit into the bigger picture?
Good question. Yeah, Weather Lab, with this specific stochastic model, seems really focused on tropical cyclones as this intense, high-stakes test case. You've got other projects like Google's Broader Weather Next, aiming for operational global forecasts, or the European Center's AI, which kind of blends physics models with machine learning improvements. Weather Lab really stands out for this open, experimental focus purely on the cyclone ensemble challenge and pushing the speed boundaries.
And the ultimate goal isn't just predicting what, but maybe understanding why the AI gets it right.
Exactly. The hope expressed is that by being open, putting the models and the historical data out there, letting the whole community kick the tires and analyze it, everyone learns faster how these AI systems are working and how to make them better.
Okay, but it can't be perfect yet. What are the known weak spots or challenges for this DeepMind's cyclone model?
No, definitely not perfect. They're upfront about the challenges. One big one is edge cases. You know, those really weird storms. Storms that do loops. Or ones that form in bizarre places like the South Atlantic where they almost never happen. The model hasn't seen enough examples of those oddballs, so it needs more diverse data to handle them better.
The atmospheric curveballs.
Makes sense. Then there's rapid intensification. The AI shows skill, definitely better than some benchmarks, but there's still a noticeable error gap, maybe 10-15 knots, in predicting those sudden strength jumps within that critical 24-hour window. That's still a major challenge.
Still the holy grail of intensity forecasting.
Pretty much. They suggest maybe hybrid models combining AI's pattern finding with some core physics rules could be the way forward there.
Interesting. Best of both worlds.
Potentially. And the third big challenge they mention is communication. This is huge. How do you take that complex spaghetti plot of 50 different forecast tracks and intensities and translate it into something clear, understandable, and actionable for regular people and for mayors or governors making evacuation calls? That's a massive user experience problem.
Absolute critical. The best forecast is useless if people don't get what it means for them.
Precisely. But on that note, they do offer some concrete things that you listening right now can actually do if you want to engage with this.
Oh yeah. What can we do?
Well, the easiest thing is just go visit the Weather Lab website. You can flip on the historical mode, pick a storm you remember, maybe Hurricane Beryl from 2024, and literally watch how the AI forecast, the ensemble spread, evolved day by day, hour by hour as the real storm unfolded. It's a really cool way to visualize the forecast uncertainty shrinking over time.
Huh, that does sound interesting. See it in action, retrospectively?
Exactly. And if you're more academic, a researcher, they encourage you to download the archived forecast data and run your own analysis, publish your findings. And for anyone involved in emergency planning, they suggest actually using the AI's ensemble output, those 50 scenarios in your training exercises, your tabletop drills. See how getting that earlier Doorknock alert might change how you'd plan logistics or issue warnings compared to just using traditional forecast products?
So bringing this all home, what's the big picture takeaway? Is AI taking over hurricane forecasting tomorrow?
No, not tomorrow, and likely not ever completely replacing human expertise or physics models entirely. It's not, as they say, a silver bullet. But it does seem to represent a really significant step, a potential game changer, and tilting the odds a bit more in our favor against these incredibly powerful and complex storms.
And like you said, even small gains, a few hours more lead time, a slightly narrower cone of uncertainty that can make a world of difference on the ground.
Absolutely. It translates directly. Home saved, crops may be harvested in time, and most importantly, lives protected because people had that crucial extra time to prepare or get out of harm's way.
And DeepMind being so open with Weather Lab, letting people see the warts and all, that feels important for moving the whole field forward faster.
It really does. It's a model for how to do this kind of research openly, invite the scrutiny, learn quickly, and iterate.
There's a really powerful quote used to wrap things up in the source material. AI hurricane prediction won't stop the next Category 5 from forming, but it might tell us 3 days sooner. And that's the kind of head start the two-day problem's been begging for.
Hits the nail on the head. It's about buying that invaluable time against the storm's clock.
So, thinking about all this, how might it change how you prepare next time a storm threatens? And maybe stepping back even further, could this kind of AI learning complex systems from vast data incredibly quickly change how we predict other big, complex natural challenges?